Hello, this is the first of the lectures that you will follow this week about the use of Lattice Boltzmann for active matter. And in this first lecture, I will concentrate on the basics of the method. I will already touch or explain you how this method, Lattice Boltzmann, is very flexible to be easily adapted to particular types of active fluids. You will see then later in the lecture today. So if you want, Lattice Boltzmann belongs to a set of models that are based on kinetic theory. And in that sense, these are slightly different from some of the ones that you have been exposed in past weeks, although there are obvious connections. So kinetic theory is a theoretical framework that provides a statistical description for the exact dynamical evolution of a system and constitute one of the fundamental branches of non-equilibrium statistical mechanics. This has a long tradition. It was, if you want to, started by Boltzmann. So we go back, jump to the end of the 19th century. And the Boltzmann equation in itself also is not a fundamental equation. Actually provides a very solid start point to understand on a mechanical basis the nature of non-equilibrium behavior of the systems, or the physics of the systems. And for example, the Fokker-Planck equation or the diffusion equations that you have already been exposed to can be derived as particular limits of the Boltzmann equation. So why is this approach useful, or what does it bring for the study of complex systems? Because initially the work of Boltzmann was focused on gases, and actually one can prove that in that limit, which limits then this Boltzmann equation become exact. But beyond that, the kinetic theory provides a systematic procedure that allows us to integrate out degrees of freedom in a systematic way, and therefore also helps to underlie clearly what are the theoretical assumptions or provide theoretical treatments that have a well-defined theoretical background on which one can build systematically. Historically, the Lattice Boltzmann emerged from a previous work done. Now we jump into the 20th century, the past century, on work based on lattice gases or lattice automata, cellular automata in a broader sense, which basically constituted a very powerful and insightful way to try to get dynamical systems with minimal rules. And in particular, cellular automata were based on Boolean algebra. And if you want, from a conceptual point of view, again, from a physics perspective, these were natural ways to extend the incredible success of the Ising model as a simplified minimal model that allow physicists to understand, for example, critical phenomena of phase transition. So then a natural direction was how we can exploit the power of minimal models to study dynamical phenomena. And I mean, if you want, in a very broad sense, the use of cellular automata can be found in many different guises or in many different applications. If you want, probably the simplest one that you have heard is the random walk. And always the idea is to have minimal rules. It's particle-based. If it's particle-based, means that we can have a proper mechanical, dynamical definition, and then they are discrete in space-time. And this also has brought these lattice gases the advantage that they are computationally very powerful, and therefore these type of approaches have also expanded and grown a lot in parallel with the fast development of computers. And because this is purely discrete, there has been, following up the work on kinetic theory, has been then the analog of how rederiving a discrete kinetic energy, kinetic theory, sorry. And that has, I mean, that's in itself a very interesting venue. And but I mean, out of all these different work done on different type of cellular automata. In the late 80s, Frisch, Haslaher, and Pommeau developed a lattice automaton that could have the properties of the symmetries that we know for fluid dynamics. And this is the lattice gas cellular automaton. The idea they had here was to have a cellular automaton that could be useful to, or that could have the minimal rules, the most simple rules that could be compatible with the properties or with the symmetries or conservation laws for a fluid. So if you want, again, it is a lattice gas model. So particles, we have particles, they move on a lattice. The sort of twist they introduced to this is that these particles had not only, I mean, the number of particles, the position on the lattice, but they had a direction. And this direction determines how the particle moves. And as such, then, I mean, this is, for example, if you have an hexagonal lattice, essentially, you have to think that each node here can then host more than one particle. So there is no excluded volume. But then if I have a particle, maybe it's easier seen here. If I have a particle, this particle in this node pointing here, sort of northeast, will move up to this other node at the next time step, which then it is here. Okay, so particles have discrete positions, discrete velocities, and then they move from one step to the next according to their directionality. And then also if a number of particles stay in a node, then there is a collision step in which they can change. For example, in this case, these three particles here will rotate to these other three particles here. So this is the collision step, in the sense that this collision mixes the velocity or changes the velocity of the particles. And then the sort of like the details of the model is about how to prescribe these rules for collision in a way that the total momentum or the total velocity at each node is conserved. So the particle number is conserved, and then the velocities are conserved. So we have mass and momentum conservation. And I said that we can have more than one particle at a given node, but there is excluded volume in the sense that it's not possible to have two particles at the same node moving in the same direction. They can be moving in different directions. And then the lattice gas is defined by what is called a collision table, for example, which lists the set of collisions that are allowed. For example, in this case, if you have two particles moving in opposite direction, the velocity here is 0. So you can go from 1,4 to 2,5 and 3,6. If you have 3, as I said, then you can't rotate. And if there is more than one outcome, then I mean, you can do that at random. And there are a number of rules. But at the end, there is a set of collisions. And that then allows you to write, I mean, this is a bit cryptic, but this mathematically defines the dynamic of the system, which tells you that if I have a particle at position r at time t with its director moving along there with velocity I, then I is like this 1, 2, 3, 4, 5, 6. Then at the next time step, discrete time step, it will move to the corresponding, this Ci now is the velocity, the vector, this vector that is drawn. So it will tell you to which node you are displacing. And then you move that, but then there is a collision part, an in and out. So a particle that is moving in direction I can end up in, I mean, you can end up in velocity I coming from a velocity I prime, another one before collision. So this would be star means after collision, then this is the outcome of the collision. And I mean, it's a bit, and this psi, if you want, that encodes this table. Okay, so that is a dynamic. So everything is well defined, mass and momentum are conserved. And then if the lattice space and velocity are properly selected, then at the hydrodynamic level, one can show that the dynamic is isotropic, so it doesn't depend on the underlying lattice. And that then brings or recovers hydrodynamic behavior from a minimal type of interaction. So when they introduced that in 1986, they thought that this could become the analogous of the Ising model, but now for hydrodynamics. And something important then, when I talk about hydrodynamics, I'm mentioning about the collective behavior. So out of this microscopic variables, then if I go to a node and I sum over all these 6 velocities, for example, in the case I was showing you, that gives you the density. If I look at the first moments, I multiply that by this microscopic vector joining nodes, which is like the velocity. You can think of this as a system that lives in a space, discrete space, because they can only move from node to node, and then discrete velocity space because there are only six microscopic velocities allowed. But if I sum over all these velocities, that gives me the momentum, so the velocity of the node, the hydrodynamic velocity at the node. And then if I do the sum for the second moment, then that gives me the stress. And then again, this is analogous to what you do in regular kinetic theory, and that allows you to link these microscopic quantities to the hydrodynamic variables, the density at the node, the velocity at the node, or the pressure, the stress at the node. And note that here in the microscopic description, we have densities or particles, and that depend on position and velocity. When I integrate, it's like a marginal, mathematically speaking, then I have variables that depend only on the node and the time. So that's sort of the idea behind this. And if you want, as I said, once you formulate theoretically, there is a solid theoretical basis. In kinetic theory, as I was referring to at the beginning, you start with Newton equations of motion, and then you move on to derive a Liouville equation, and from the Liouville equation, you can arrive at the Boltzmann equation, and from there show that you can get Navier-Stokes equations, so the equations of motion for a liquid. Actually, it was possible after this was the lattice gas or automata was introduced in 1986. Then there was a body of theoretical work that showed that you could follow the same routes, but now doing it on a lattice. So you could start for a lattice gas, derive what would be the equivalent of a lattice Liouville for this minimalistic model. From there, get by pre-averaging a lattice Boltzmann, and then eventually go back to the Navier-Stokes. Okay, so that's what I was referring to in the first slide as the power of having the kinetic theory framework underlying these models, that you have this systematic and well-defined procedure to go move up and down in a rigorous way. Now, lattice gases were very, I mean, there was large expectations. Even they feature, there were articles in New York Times saying that this would be the way to solve the turbulence problem, but there are drawbacks actually, because there is a lattice that breaks Galilean invariance. There were problems of Galilean invariance and well-behaved value for the pressure, so that led to also a lot of works that to some extent solved them, but there are still issues. And also it's difficult to, in order finally to go to a high Reynolds number for turbulence, then you need to be able to tune your viscosity to very low values, and that was also difficult. There were issues, I mean, a lot of noise. So all in all, at the end, didn't deliver as much as it was expected from a practical point of view, even if computation is very efficient. But conceptually, it opened this venue to the proposal of models where you can handle or control get say hydrodynamic behavior in the appropriate limit, but working at an intermediate level in a well-defined theoretical environment. So after this, then now I wanted to describe this just to give you theoretically or conceptually how this lattice Boltzmann emerged. So later on, I will talk about how lattice Boltzmann works, and then you could think that you can understand or use lattice Boltzmann as a bona fide kinetic model without having to worry about all this historical perspective. But I think it's good to put it in, because it gives value to the fact that this is a proper kinetic approach. It's not just an effective way of solving. I mean, it is used in many times as a way to effectively or, I mean, efficiently solve the hydrodynamic or the Navier-Stokes equations, but it's more to that, because there is really a proper fundamental kinetic approach that you can exploit to your advantage, both computationally or to extend it or to apply it to other type of situations. I think it's worth at least knowing where does this come from. But I mean, all in all then, from that perspective, and that's how lattice Boltzmann actually was first explored, if we have these densities for these lattice gas cellular automata, if I average many of them, so an average means I can imagine like many realizations of these lattice gases, and then I do an average over configurations at a given time, then what is a Boolean variable, Ni, in the lattice gas is either 0 or 1. I have one particle at a given node moving in one direction, or I have none. If I do an averaging now, I will have still, I will look at how many particles I have at a given position moving in a given direction, one of these 6 directions in this case. Well, here is 8. But then the average is no longer a Boolean variable, because I do averages, and then in some configurations there will be a particle, in some others there are no particles. So this strict excluded volume constraint that I was referring disappears on averaging, and then now F is a real number. So you should think of it as the density, or if you normalize, as the probability that I have a particle at a given node moving in a given direction. So that is a pre-average. And then also when it comes to the, so I can then formally get the equation for the cellular automata that I was showing you before. I can average here. I will have here the Fi at a given node at t plus 1, Fi post-collision at the previous time step. And then I have to average now this collision operator over these, all these possible occupancies of the lattice. And that's, I mean, there is no free lunch, yeah? So that's where you have to pay, because this average is, I mean, you can do it formally. It's not easy to, it's non-linear, so you cannot have an explicit expression for it. And that's basically, at the beginning, all the work done on Lattice Boltzmann was, well, let's do this pre-average in different ways. Let's construct effective collision tools. And that was something that had to be done numerically. It was quite costly computationally. So at that stage, at that time, Lattice Boltzmann was a conceptual nice idea because of this connection with kinetic theory that I was telling you, but it was not something or a tool or a method that would be useful. And then a step forward was introduced by Francisco Higuera and Sauro Succi when they start thinking about how to handle this collision operator. And actually, again, in kinetic theory, you have to face the same problem. In the Boltzmann equation, dealing with the collision operator is not easy. And there were approaches from the 60s in ways to approximate this collision operator. And in particular, one of the approaches to linearize the collision operator. So what does it mean, linearize? So if we assume that the distribution function, this F is the distribution function, the one particle distribution function, is not driven very far from equilibrium, because we know what is the equilibrium distribution function, then you can linearize in deviations, and then you can linearize this collision operator. And then if you linearize, then you can write something explicit that you can exploit. And that's basically what Higuera and Succi had the thought of also introducing in this Lattice Boltzmann approach. And that was really a deal breaker that changed completely the perspective on Lattice Boltzmann and how it sort of like freed it from this cumbersome need to be linked to the, if you want, this is like the microscopic view. This is the equivalent of an microscopic potential. And then in a way, people were trying to do this averaging so that then the collision operator for the Boltzmann equation would be linked to these microscopic rules. And then what Higuera and Succi said is, well, look, if we want something minimal and simple, there is no need to keep this clear link. We can have an effective collision operator with the proper symmetries. Then it's not linked to a particular collision set of rules. So we lose that, but then we gain in much more powerful method, because now it's possible to prescribe a priori this collision operator, and then Lattice Boltzmann become a much more efficient and powerful computational tool.